In this lecture, we want to talk about degree of isogeny from the perspective of algebraic geometry. So in algebraic geometry, we have this following correspondence. You have this rational map from one curve to another, and this induces one-to-one correspondence, gives us a contravariance from function field of C2 to function field of curve 1. And we have discussed many such examples in our lectures on algebraic geometry. So then you have this degree of extension for this field kc1 over phi star of kc2, and this you say is degree of this rational map phi. So we want to carry the same notion to isogeny. So we want to carry this notion to degree of isogeny of elliptic curves. So again, you have map phi e1 to e2, and you copy this thing right here. So instead of c1 and c2, we are writing e1 and e2. So this we will say is our field extension, is our degree of field extension is degree of our isogeny. But we have been saying till now that the degree of isogeny, if this phi is given as a rational map like this, p over q s over t y, then the degree of this isogeny is precisely maximum of the degree of the numerator or degree of denominator. So maximum of degree of numerator or denominator of this first fraction. So we want to show that this notion is same as this notion. So this problem is simplified by using such a commutative diagram. So we want to talk about this commutative diagram. So in this commutative diagram, what we are trying to do is we are trying to take our difficult problem, that is talking about degree of our isogeny from elliptic curve 1 to elliptic curve 2 to some projective space p1 to p1. And what we need to do first is we need to construct a degree 2 map from E1 to P1 from here and here. And you know that these maps are all rational. So when you multiply them or compose them, they will just compose nicely here and here. So this notion will carry over here precisely. So the only thing we need to do is that we need to talk about this degree 2 map in some detail. And then we need to talk about that here this degree of phi, the field extension, will be same as the degree of the morphism. So first let us talk about this degree 2 map. So this degree 2 map is given by the Weierstrass P function. So Weierstrass P function we will write in a simpler form 1 over z square plus O of 1. So there are other terms here, but we are writing it as O of 1. So this Weierstrass P function essentially gives us a degree 2 map from the elliptic curve to the projective line. In fact, these elliptic curves form a double cover of this projective line. So from elliptic curve E, y square equals to x cube plus ax plus b, we can have this map xy to x. Now this is a double cover, and it is ramified precisely at 4 points. You have the point at infinity and 3 roots of this cubic equation. So 0 equals to x cube plus ax plus b. And this double cover you can see for every value of x. So you have a y square here, you have 2 values for y. So this is our standard double cover. So elliptic curve forms a double cover of P1. So and this is of degree 2, which you can see from the Weierstrass function. So this is done. So now we just need to carry this problem to here. So consider the following morphism given by a polynomial. So say polynomial f in k of x. This lies in the function field of the projective line k of x. So again, now we construct a map this phi from p1 to p1. So 1x. So here the points are written as 1x. It is carried to 1fx. So f basically is taking p1 to p1. It acts on this point x. You go here. So once you have this map f between p1 to p1, we will have extension of fields given to us like this. So this thing is precisely carried over from here. So for corresponding to p1, you have this. Here also the field is k of x, but since you have multiplied by f, you are injecting this into this. So f is just a polynomial here, so this will become k of f. So this is important to notice. This is like this. So we are saying that this is precisely equal to degree of f, and this will follow from our standard division algorithm as we do in Galois theory about fields, and it becomes more clear if I give you an example. So say f is x square, then you can see that degree is 2, degree of f is 2. So then you can see that degree of field extension kx over kx square is also 2. You know, your basis of extension is just 1 and x. On the other hand, you can say f is xn, then you have kx over kxn, and again you will notice that our degree of extension is n. So it is precisely the degree of the map. Now what about rational functions? You can think of it as dually. Instead of x square, you can think of it as x minus 2. Again, proper thing would be to use standard division algorithm, but heuristically you can see that the basis would be 1 and 1 by x now. So again, if the polynomial f of x is px over qx, just like this, then we have to use Euclidean division, because in this field you will also have rational functions. So you either have to divide by the numerator or the denominator. So if it is a rational function, say h1 over h2, then you have to divide it by f over g, or in this case p over q. And again, the maximum degree would matter, and that's what will form the basis. So degree of f would be maximum degree of px or degree of qx because of the division algorithm. Now this proof to me was non-trivial, and I could not find it myself. So sketch proof was received from Professor Silverman via email, and I hope I have essentially understood his argument and produced it correctly here.